Okay, thank you very much. Uh, oh, we will start with Arda. The four of us who were the modelers will be presenting the basic results of this. And Arda, could you please?
Sure,
Oh, will
Sisi.
not,
So, can you see my screen now?
yes, excellent.
Okay. So this is the chapter one is a multidisciplinary and multinational effort. You can see the many contributors listed in this chapter. So we are only on behalf of them, we are presenting as the coordinators in this chapter. So I will be starting with the introduction. Before we start, I should tell in three languages to say hi, kalimera and merhaba to make it a little bit less informal. Okay, so let's start with the tectonic setting. The earthquake is located in a region where basically extension is dominated due to the rollback, the northward subducting African slab. Slab is basically retreating towards south, and this creates an extension. Also creates results in tectonic escape of North Anatolian plate towards west. So it's a pretty complex region. We have also low angle detachment faults in the region, plus we have some transfer fault zones and different plays, southern plays of North Anatolian faults. So if you look at the seismicity through the catalogs, you can see the widespread seismicity, and it's a very elevated seismic activity in this region. So you can see along the grabens and horst and graben structures, we have concentration of seismicity. Also, we have North Anatolian fault passing here, and their southern branches is dominating these clusters. So if we look at the focal mechanisms, if we start looking at the mechanism only in terms of strike slip mechanism, you can see most of these mechanisms are associated to North Anatolian fault and its southern branches. And you can see the activity is pretty severe. For the people who are not familiar, these type of beach ball type of plots, it's basically representing, in this case, 4 quadrants is representing almost pure lateral motions. If you look at from the catalogs, compiled catalogs about the extensional mechanisms, you can see in reddish colors, you can see these mechanisms are also along the grabens, and you can see it's more or less northeast, north-south extension is indicated. So we are in the star represents our earthquake location, and you can see both mechanisms are dominating the region. So both strike slip motions and normal faulting motions, extensional motions are both active, coexist in the region. So if we come in a close-up to the Samos earthquake, which is close to 7 magnitude, you can see the star represents here. We have some discrepancy in the magnitude because of the agencies in the figure versus the title, but it's basically close to 7 magnitude earthquake. You can see it's occurred in a region where it's both strike slip faults and normal faults are active and causing seismicity. And from the Harvard solution, you can see the focal mechanism solution. This Harvard solution indicates clearly a pure extensional mechanism for this particular fault. So in this, depending on the fault mechanism, we are basically eliminating the strike slip faults as the source of this event. Mainly normal faults should be the source. And if we cut across the focal mechanism, this is a stereographic plot. If you cut across it, you can see a section like this, which would be indicating two possible fault planes that might be activated during the earthquake. So we would be needing, in order to decide if it's a south dipping or north dipping fault plane, we need other independent data. And further, during the presentations, we will acquire those. So here, also this data, in order to identify which fault plane is activated, field data is crucial, vital. And in that sense, we had teams from both sides, from Greek partners and Turkish partners, that have field work conducted on Samos Island and Turkish coastal area. So in the Samos Island, we can see there are Identification, co-seismic surface deformations is identified in Karlovac region. You can see northeast, southwest directed rupture-like features, possibly secondary, but it's very clearly in the system. Plus, we have permanent uplifts detected near the Karlovac. Also, we have mass motions. Here is an example in Ablaki region where you have a steep slope, and also liquefaction features have identified in Samos Island. In Turkey, we had conducted field survey across the coastal section nearby the earthquake area, and we identified that no surface deformation had occurred or reached to the mainland, Turkey. So, but we clearly identified uplifted terraces indicating rapid uplift due to tectonic motions faulting. Plus, we identified normal faults which are active. You can see the very nice outcrop. You can see the motion directions identified by arrow indicating downward motion dominated. And here is another outcrop near Ephesus, antique city, very close to it, which is also an active normal fault. Also, we have the strike-slip fault that has been recently activated anyway. Also, you can see in the arrow this lateral motions, which indicates that this fault is mainly dominated by lateral motions, so strike-slip. So one thing emerged from this earthquake is basically the most heaviest damage is occurred in the metropolitan İzmir area. So to upfront to give you a kind of a summary on the tectonic setting of İzmir will be timely. You can see this is the area where most of the metropolitan area is located. And you can see it's basically composed of Bornova plain, which is the basin bounded by two northward and from north and south, two faults, which is İzmir and Karşıyaka faults. And you can see in the photo, their outline is pointed in the photo here. And an important aspect is here is where the most damage is occurred, this area in yellow. And this area, according to the Holocene records, was one time was partly covered by sea. So it was a saturated region. Plus the gravity modeling along with the boreholes identified that the basin field that is located in the İzmir is significantly thick and results in very low shear wave velocities, which would be a part of contributing on the ground motion. So that will be a concern of other presentations. Okay, just to make sure that since İzmir get afraid a lot, because this was a distant event, almost 70 kilometers away from the metropolitan area, but there was a heavy damage. So we should look into the seismic history. You can see along the area, there are many active faults that are forming normal faulting and strike-slip faulting at the same time. And if you look at the historical records, we see that İzmir Bay area is even more heavily plotted. So elevated activities can be identified. And the heaviest damage was occurred in the 1688 event. It was a very large event and also created some tsunami waves. So you can see in the history of İzmir, the earthquake damage is pretty common. And at this point, we have lots of unknowns related to the active fault. So first of all, in order to identify the realistic risk realistically, we should identify the faults which are active. Then we should work on what is the motion rate on those faults and also how much stress have been loaded, what was the reoccurrence intervals along these faults. So we should do a lot of research to identify which are the ones that are posing imminent risk in that sense. So at this point, I will give it to Kostas to further continue with the presentation. Let me share.
Okay, thank you, Arda. I hope you can all see my screen. Is that okay?
Yes.
Okay, perfect. Well, hello also from me. Thank you, Arda, for the very nice introduction. I'd like to thank the organizers of this meeting and of this volume. I have to be embarrassed, but it's one of these cases where something very nice cooperation between the Greek and Turkish seismologists started by engineers and not seismologists. This is pretty nice, and I'm embarrassed to say that we should have done a better job in the seismological community, but thanks anyway for the opportunity to work closely with the scientists from Turkey. So what you're seeing here are the 4-place solutions published from different institutes after the earthquake. As you can see, earthquakes magnitudes are between 6.9 and 7.2 with a median value of 7. Very small variability between the different 4-place solutions, and the epicenters, although they are distributed over a very wide area, which is kind of typical for the accuracy of these things, there are essentially no differences. So the moment magnitude of this earthquake is clearly 7. And an obvious question is, where did this earthquake occur? So we can start from the epicenters and the 4-place solution, which are not enough. And to answer where there's a fault and why the earthquake occurred there, we need to review a large number of data. The first thing you may want to look at is our active faults, and I'm just showing here results from different databases. This is the Gredas database from Zboras 2012 and Caputo et al. 2012. As you can see, there's already a fault in the north part of Samos, where you can more or less see this fault coinciding with the earthquake epicenter. This is the NOAA database from Ganas and colleagues, which shows a very large, well, it's not a fault, it's like a fault zone digitized over there. And that's from another publication from Sakellariou and Tsabourati Karaounaki, which is showing kind of different faults, but essentially there are faults in the northern part of Samos from published databases. And this is the faults on Samos from the tectonic map. Essentially, they are mostly showing similar faults on land. So you can rely on this information to have an idea about on which fault this earthquake occurred. And clearly, you had the candidate fault, which is right here, from whatever database you look at, that could host an event like the 7 magnitude event that occurred. Naming a fault is not always easy. It has been named as Karistrios fault in previous publications and North Samos fault by Hadjipetros et al. We picked the first but more difficult to pronounce Karistrios fault for the volume, which I'm going to use here and after. So the next thing you can look at is historical seismicity near Samos Island. In some cases, there are detailed information. This is an earthquake that happened in 1955. And you can see that the epicenter is in the broader delta of the Buyuk-Menderes area river. And it caused damage both into the Turkish side, but mainly in Agathonisi and to a less extent in Samos. The most significant damage observed was in Agathonisi, south of Samos, and there was distributed damage in Samos and other areas, and with maximum intensity around 8. And also, similar to this event, there was a tsunami wave that was observed in southern Samos with a maximum height of 2 meters that entered land to the distance of about 20 meters at several places. So very, very similar, but on the southern coast of the island. And very similar also in the sense that it had very weak shocks and very weak aftershocks. The largest aftershock was 5.1. So quiet aftershock sequences are not something very rare in the Aegean. They have happened in many other cases also in Samos. You can use modern tools to kind of try to simulate the distribution, and you can do a best fit between observed and predicted damages, intensities. This is a finite fault stochastic simulation modeling that shows that you can more or less fit the data. These are the synthetic and these are the observed macroseismic information with a fault at the southern part of Samos deep into the south. So even with this historical data, sometimes you can do a decent work and propose a candidate fault that could host this event. And clearly you can see the most recent event in the area happened on a fault that was most probably in the southern part of Samos. With older events, it's not as easy because the information is much more limited. This is the 7051 6.8 earthquake that damaged the area of Athi and Chora, intensity around 8, also Kusadasi, and practically completely destroyed Azakli on the Turkish coast. Whereas in the Dilek Mountain, there were significant rock falls and fissures, strongly suggesting that this event did happen closer to the Turkish side rather than Samos. And you can have a rough idea about where this earthquake occurred. It appears to be a 6.8 earthquake because it was felt at very significant distances inside the Turkish mainland. Reviewing all the historical seismicity for Samos, you end up essentially with a figure like this. Samos had a very peculiar history in the last 250 years, with a very large number of events between 1831 and 1873, which happened most of them on land. So a series of earthquakes in 1931, 1846, 1865, and 1868 on land, with a lot of rockfalls, fissures, and localized damages. Then seismicity moved to the north. This 1877 event is most probably on this fault because it damaged very locally two villages here. There were ground fissures. This 1873 strong event, which also inflicted some damage on İzmir, may have happened on the eastern part of the fault. Keep that in mind because it correlates very well with the slip of the 2020 earthquake. So essentially, you had an intense seismicity during the 19th century, which culminated at the 1904 6.8 event that clearly occurred on the island and destroyed all villages along the fault and inflicted heavy damage all around the area. The 1855 event occurred in the south, so suddenly we have another major fault here, the Kaisios fault, which hadn't ruptured definitely for more than 250 years. Most probably the previous earthquake there was around 47 AD, but that's another topic. So this information can also help you, and you can also use additional information. This is results from raw data from swath bathymetry collected after the earthquake by Nomikou and colleagues, and you can more or less see this very steep slope on the northern side of Samos. This is from looking from north to south, so looking towards the northern coast of Samos Island. You can see a big landslide over here, and you can more or less see the geomorphological evidence for the presence of the fault in the northern coast of Samos. But critical information also came up from INSAR observations. This is the broader image INSAR picture that was produced a couple of days after the earthquake, which clearly shows this blue colors here, the uplift on the footwall, and this yellow colors over there, which shows subsidence. But if you take a very close look at the distribution on the island, you see that there are some red colors over here and some yellow colors over there. Essentially, this just tells you that the surface projection of the fault should be somewhere there, suggesting that the fault may have not really reached the surface because displacements are not very large, but it's very close to the northern coast and it's dipping towards the north. Of course, the final information about the fault comes from the aftershock sequence, and these are the preliminary first results that came a few days afterwards by the precise location from Papazachos and his team in the University of Athens that showed significant concentration of earthquakes on the eastern part of the fault and some clusters far away from the fault on its western side. Just to give you an idea of how important cross-border collaboration is for this kind of work, we did also a relocation framework of this volume, and I started from the data in my lab, which we had at that time approximately 1,000 events involving 10,500 faces. If you add the data from the National Observatory of Athens, we ended up to 1,000 events and 17,000 faces. And if you add the data from Turkish colleagues from Korea, Afad, and from the University of Athens, you end up with 1,300 events and 31,000 faces. We don't have a mechanism, except perhaps for EMSC, for the real-time data exchange. And I think this earthquake points out that we need to strengthen this kind of collaboration for an efficient response after an earthquake. If you use all this data to relocate the events, these are approximately 1,000 events. This is the picture from the first day. You can immediately see this gap of seismicity over here. This is 1 week after the earthquake, where you see again this gap. Some earthquakes have occurred right here, and then you see some secondary clusters appearing on smaller faults where seismicity has been triggered. So that thank God the seismicity was moderate and not that strong. And this is the situation 1 month after the main shock. So again, this area has pretty sparse seismicity, but you have significant clusters outside the main shock. Here, this cluster here, which is along the lineament that you can see in the basin, and a large number of earthquakes towards the Turkish coast. If you look at the distribution of aftershocks 1 day after the earthquake, you see this is the main shock epicenter, this is the stronger aftershock. This is an along fault projection, this cross-section A1 to A2, and you see this big aftershock gap, which we still see even 1 month after the earthquake, although some seismicity has crept in. And finally, if you look at cross-sections, this fault here, this cluster here appears to be more or less of like a vertical fault, most probably related to this lineament here, like a strike slip fault, and Ali is going to talk about this in the following. And if you look at the cross-section right here from C2 to C1, this is not a very good image, but it definitely shows a dipping towards the north, towards C2. When you go into the towards the edge of the fault, towards the east, you get a very diffuse distribution. This will improve in the future, but this also points out to triggering of secondary faults at the edge of the main fault. Thank you.
Ali, thank you, Kostas. Ali, Pinar?
Okay, yeah, I can hear you now. Okay, I hope you can see my screen. Okay,
Yeah.
thank you. Thank you, Kostas, and thank you, Arda, for the nice presentations. And I will present the aftershock focal mechanism. I will talk about the GPS data that was obtained following the main shock. And also, I will give some information about the interferometric and GPS modeling. First of all, let's start with the aftershock mechanism. Here in the screen, we see the aftershocks of magnitude larger than 3.7. And most of the aftershock, as you can see, are normal faulting, showing normal faulting mechanisms. In the aftershock area, we can notice distinct area. One of the areas is the area where no aftershocks occurs, and the other two areas is the area where dense aftershocks or dense focal mechanisms are obtained, and the other area that is located in the west side of the source area is the less active or the aftershock with less density. And the major aftershocks or the largest aftershocks actually took place just in the area between, in the boundary of no aftershock area and the intense aftershock area. And in the next slide, you will also see that there are some reasons why the major aftershock took place in the boundary between no aftershocks and dense aftershock area. And actually, this boundary is also the boundary where, to the west of that boundary, a distinct uplift was observed in the island, and to the east, especially in the northern part, subsidence have been observed. So this boundary is also could point the boundary of subsidence, and uplift also can give some information about this. And as Kostas mentioned, these are the aftershocks that were obtained only in first 2 days, I think. And the major aftershock took place just an hour after the main shock. And as Kostas mentioned, we should improve the mechanism of data sharing. Already such data sharing exists, but still there are some rooms to be improved. And those are the mechanisms that were obtained by the Greek colleagues. And the next mechanisms that I will show are obtained from Turkish colleagues and using the Turkish data. And as you can see, there are similarity and some differences in the data. Surely, if we share the data in real-time mode, and especially after the main shock, we can obtain more robust solution, I can say. And in the second map of aftershock distribution, we can see that several strike slip mechanisms emerge along with the normal faulting mechanisms. And why the strike slip mechanisms are taking place with the normal faulting mechanisms? Probably this is a question that should be answered in the context of geodynamics, because when we try to model the stress changes associated with the main shock, and we notice that the area of optimally oriented strike slip and optimally oriented normal faults actually coincides. So in the stress, I mean, within the stress tensor that is acting in the region, both the strike slip and both the normal faultings are favorable for rupture. And that's why the coexistence of normal and strike slip mechanism actually is not a surprise. Using the focal mechanism, we try to establish the stress tensor acting in the source region of the Samos earthquake. And what we found is north-northeast, south-southwest extension. Actually, such extensional regime is dominant in the Aegean. We have seen such extensional direction also during the 2017 earthquakes in Karaburun, and also we have observed such extensional direction in Bodrum and other Aegean Sea earthquakes. And what is important here is maybe there are some evidences that most of the mechanisms that are shown in the high density aftershock area are actually taking place on off fault. And the on fault mechanism, there are just a few on fault mechanisms existing in the area of low aftershock area. And this probably is pointing out, this probably could be an evidence indicating that the stress drop or the moment release was completely associated with the main shock rupture. And especially to the east of the epicenter, the reason why the aftershock density is very high is probably Anastasia will mention about the causative why the aftershock concentrate in this region. And I will briefly say that probably the slip associated to the east of the epicenter was smaller compared to the area west of the epicenter. That could be the reason why we have such an uneven aftershock distribution. And using the stress tensor, one can obtain also the optimally oriented faults that were affected by the main shock rupture. Here, it is indicated a Coulomb stress change associated with the main shock fault rupture. And in this figure, actually the slip is assumed to be uniform, and the fault length is assumed to be around 35-40 kilometer length. And because of this uniform slip associated by the main shock, we can see stress loading at the tip of the ruptured fault plane, and most of the aftershocks are located in off-fault fault. And just a few aftershocks are taking place on the ruptured fault plane. And actually, we know that the aftershock tend to occur at the location where the stress is increased by the main shock. And we know that the stress was completely released by the main shock, but although we have such a stress release, we still can observe some aftershocks on the ruptured fault plane. And the reason for this is maybe, or could be explained by the variable slip model. But before going to the variable slip model, also on the upper left corner, you'll see a cross section along AB profile. And here you can clearly see that the stress from the surface to a depth around 13 kilometers was completely released. And the depth below 13, 15 kilometers, we can see that stress is increased, and probably this stress increase caused by the main shock will be released by post-seismic slip. And actually, the aftershock that took place on the ruptured fault plane can be explained by the variable slip model. In the variable slip model, there are some differences on the slip values that are obtained from several grids, and the fault plane is divided in several grids that have different slip values. And because of this slip difference between the grids, here you can see that there are some red areas pointing out a stress increase on the ruptured fault. And this is probably the reason why we observe also aftershocks on the fault where the stress was completely released. And actually the comparison between the variable slip model and the aftershock location, one can see that most of the aftershocks in this figure, the red histograms indicates, the red bar indicates the number of aftershock that are locating at the area of increased stress, and the blue one are taking place in the area of decreased stress. And about 75% of the aftershocks are located in the area of increase, and just 25% are located on the ruptured fault plane. Okay, here are shown the GPS stations that are operated by Greek and Turkish colleagues. And the azimuthal coverage of the GPS station, as you can see from the figure, is quite good to obtain a source model that is based on GPS data and also incorporating the interferometric data. In this figure, you can see here that the length of the red arrow here indicates a motion of 5 centimeters, around 5 centimeters. And here we can see that the motion at Samos GPS station and in Çeşme GPS station is around 5 and even a bit higher than 5 centimeters that move to different direction. The GPS data clearly indicates that the Samos Island moved southward, and in Çeşme İzmir station moved northward, indicating that the fault is dipping northward, and the Samos Island is located on the hanging wall. And in the next slide, here actually the largest motion was observed at Samos stations. And on the right, you can see the horizontal motion that is observed at Samos station. Here we can see that the east-west component, the motion on east-west component is about -6 centimeters, indicating a motion about 6 centimeters westward, and around 37 centimeters that is observed on the north-south component, -37 centimeters indicates a motion toward south. So the largest motion was observed by Samos stations. And here the GPS data shows just the horizontal motion. And because of low constraint on the vertical component, no data is shown here how the vertical component motion was. just the vertical motion observed at Samos station is indicated here. And the Samos station clearly indicates a motion around 8 to 10 centimeter uplift that is observed at Samos station. And on the left, you can see figures indicating such motions, or maybe also there is a component of strong shaking that may cause also a subsidence.
Professor Kiratzi and Professor Pinar, our time is completed. Even we use the 10-minute question and answer session time. Would you please kindly wrap up your presentation?
Okay, thank you.
Thank you, Professor.
I will take up right now, Ali, to close the session, okay? With one slide. Is it okay?
Okay, just show the uplift regions, okay?
Yes, okay.
And as I talked, the star indicates the hypocenter, and to the west of the hypocenter, where the major moment release took place, uplift was observed, and to the left of the hypocenter, or that's say to the east of the hypocenter, we can see some subsidence in the north part of the island, and that's why the boundary actually is crossing from the hypocenter. And in the bottom, we can see the a model that is indicating how an uplift is associated with as an elastic response caused by the main shock rupture.
Thank you, Ali.
Okay, go on.
I will go to my last slide because we don't have time to show the finite fault models, and I will jump directly to it. Do you see my screen?
Yes.
Okay. This is, I was going to show the final fault models, but it's no problem. I will go directly to the last slide, which shows the earthquakes that we had in the Aegean area since 2006. There are 24 earthquakes with magnitude over 6, and you see them all around here. What is important is that we have 6 earthquakes in the cross-border region with Turkey. You see them, and this area here encompasses 2 7.0 earthquakes, which is the 2014 earthquake and the 2020. Which means that since 2006 that we had this, and 2008 that we had this deep focus earthquakes, there is an unclump of the deformation in the area. So there we have an accumulation of strain, we have significant increase of seismic hazard, and significant increase of seismic risk, especially in urban areas. Because there is a chance all around the Aegean plate for an earthquake anytime, anywhere. And the risk is increased when the earthquake is close to an urban, densely populated area. So with this concluding remarks, I'm sorry I didn't have time to show the finite fault models, which are very crucial for the engineer community. I will pass the floor. If there are any questions, we will be happy to answer. Otherwise, I will pass the floor to the next session, which is the tsunami effects and performance of port structures. And the moderators are Professor Galciner, Caligieri,